In this chapter, we will be looking at permutations, combinations, and the binomial theorem. In this lesson, we will be looking specifically at the fundamental counting principle.
So we begin this chapter looking at something called the fundamental counting principle. Now, the beautiful thing about this thing is and it's true of a lot of topics in math, that the longer the name, typically the simpler the idea. And here we go. The fundamental counting principle is very, very simple at its heart here. If you're trying to accomplish a task, and it can be broken down into a couple of, like, let's say, subtasks. Okay, like let's say you're going to go choose an outfit. Well, you have to choose a pair of pants. You got to choose a shirt, right? The number of ways the whole task can be done is simply the product. Okay, is the product of the number of ways each subtask can be done. Okay, so again, we take a task, we break it into a number of subtasks, and then however many subtasks there are, we look at the number of ways we can do this one, we multiply it by the number of ways we can do this one, multiply by the number of ways we can do this one. That's the total number of ways the whole thing can be done. Now, if that's not abundantly clear to you right off the top here, it'll make sense after a couple of examples, so just hold on.
A school cafeteria offers sandwiches made with fillings of ham, turkey, cheese, and egg. These can be put on white, multigrain, or rye bread. How many different sandwiches can be made using only one filling?
Okay, so there's a couple of different ways we can do this question to figure out how many sandwiches we can make here. And one way to do it is the tree diagram here. So this is what we do here. We start off with this idea. We're going to build a sandwich. Okay, so we have a choice. First of all, we could choose either a ham sandwich, turkey, cheese, or egg. Okay, now from there, all of these choices. Now, you can make a choice here, but we're going to just look at all possible choices here. Okay, here they are. Each one of these leads to another choice that has to be made. Do you want it on white bread, multigrain, or rye? So here are the types of sandwiches we could make here. We could have a ham white, a ham on multigrain, and a ham on rye. We could have a turkey on white, a turkey on multigrain, a turkey on rye. We could have a cheese on white, a cheese on multigrain, a cheese on rye. We could have, finally down here, our last choice of sandwich here, our egg on white, our egg on multigrain, our egg on rye. Now, we have just listed off all of the different possible choices that you could make. Okay, there are no other options here at this particular cafeteria. So now we've turned this into a counting problem. We can just count this out here. That's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 sandwiches. Okay? Now, that's one way of figuring it out here. Another way of figuring it out is to do this. Okay? We've got two subtasks here. Okay? We have to choose the sandwich. Sorry, we have to choose the type of sandwich and the type of bread. We have got 4 choices for the type of sandwich and 3 choices for the type of bread. The product of 4 and 3 is 12 different sandwiches. Okay? 2 ways of doing it here. This is nice to kind of illustrate the idea, but please, you don't want to be doing this every question here, particularly if we get into questions where you've got lots more choices, thousands of different choices here. Okay? This is how we want to start approaching this problem here, by simply breaking it into a multiplication problem. That's what we want to do. This right here is the fundamental counting principle.
A car manufacturer offers the following options on a particular car that can be special ordered: 2 doors, 4 doors, 6 different colors, electric, gas, hybrid powered, air conditioning or no air conditioning, sunroof or no sunroof, and finally leather interior or fabric interior. How many different cars can be ordered?
Okay, so when we read this problem, what we need to do is figure out what the subtasks are. The task is to choose a car. Okay, there are a number of subtasks here, though. First of all, we have to make a choice here. Is it going to be a 2-door or a 4-door? Well, how many choices do you have there? Well, just the 2. So we've got 2 choices. This is doors. Okay, there's one subtask. And now we're going to multiply it by the number of different ways we can choose. The next subtask here is to choose colors. And we're told there are 6 different colors here. So here's our colors. So two different ways I can choose the number of doors, 6 different ways I can choose the color. Beyond that, I have the choice of electric, gas, or hybrid. Well, okay, I've got 3 choices there. So there are 3 ways that I could satisfy that subtask. So this is the engine. Okay. Next, what's my next choice here? Well, I've got air conditioning or no air conditioning. Okay, that's AC. There are 2 choices there. Okay, yes or no. Then we've got sunroof or no sunroof. Again, 2 choices here. 2 ways that I can complete that subtask. And then finally, we've got the choice of interior, leather or fabric, and there are 2 choices there. This is the interior. Now, in a lot of cases, that's actually as far as you need to go. Quite honestly, there's a lot of times when you're answering these problems where that's all I need you to do is even write out the statement. I don't even need you to evaluate it here, but we will. We're going to evaluate this. So 2 times 6 times 3 times 2 times 2 times 2. Well, there are 288. Okay, there are 288 versions of the car. Okay, that you can order here. A lot of choice.
In how many ways can 5 different black cars and 4 different red cars be parked next to each other in a line if a black car has to be the first in the stall on the left and a red car has to be the last on the stall on the right?
Okay, with this question here, we're throwing in a bit of a restriction here. Okay, we're choosing the cars. We're going to put them in order, but we've added a couple of little details to the problem here where the first car that I choose on the left has to be one of the black cars, and the last car on the right has to be one of the red cars. So let's think about what those tasks are, and let's deal with the restrictions here, the specific restrictions implied first before we deal with other things. So on the far left-hand side here, I've got to put a black car. Well, I've got 5 to choose from. Okay, so my task is to choose one of those. And I will end up multiplying this by the other cars here. And there's going to be 9 of them. Okay, now way over here though, I'm going to multiply by the number of cars, the number of red cars that I can put over there on the far right here. And it turns out there are 4 to choose from. Now I'm choosing those guys first. Okay, I'm dealing with the restrictions first. In fact, we might even make a little note over here. We're going to deal with restrictions first. Okay, deal with restrictions first. So those 2 subtasks needed to happen before everything else here. Now, once that's been dealt with, the next subtasks here are going to be just putting individual cars in those places there. Now, at this point here, how many cars have I got left over? I had 9 to start off with. I've chosen 1 to go here. I've chosen 1 to go here. That means there are 7 cars left over. So my next task is to choose one of the 7 to go here. My next task is to choose one of the remaining 6 to go there. And then choose one of the remaining 5. And then 4, 3, 2, 1. Okay? And so now I've completed all of my tasks, all of the subtasks here. We will multiply this all out. Just going to go to my calculator, do this real quick. And turns out that's a whole bunch of different ways that this can happen. That is 100,800 different ways they can be ordered. These can be ordered. It's interesting. Actually, it's really interesting how very quickly the number of options, the number of ways you can do this grows with even just a very limited number of objects you're working with.
Using the letters from the word equation, determine the following number of arrangements if all the letters are used.
Okay, so in this first question here specifically, it's saying that we're going to use all of the letters. Okay, well, how many letters are there in the word equation? 1, 2, 3, 4, 5, 6, 7, 8. 8 letters. Okay. With nothing else being stated, with no other restrictions imposed in this problem, my task is to choose which one. My first task is going to be to choose which one comes first. Well, I've got 8 letters to choose from there. Okay. After that, how many letters am I left with? Well, I've got 7. Okay, and then how many? Well, then I've got 6 to choose from. And you should be seeing, the pattern coming up here. This is just going to go down. Every time we choose, we're going to lose. Okay, we're going to lose another choice there. So all we got to do is multiply all the values out. Basically, every number from 8 down to 1 becomes a factor of this value. And when you multiply those all together, you get 40,320 different ways that we can arrange the words in the letters in the word equation without any restriction imposed on that. There you go.
4 of the letters are used.
So now this question is very similar to the one that we just did, except in this case we're told that we're only going to use 4 of the letters. Now, that means we've got, if you want to think about it in terms of, again, like our fundamental counting principle says about dealing with different tasks, that means we've only got 4 tasks to accomplish here. There's the first letter that we're going to look at, and the second, third, and fourth. But remember, there are still 8 options for that first letter here. And once you've chosen that, there are then 7, and then after that you get 6, and then 5. But I'm going to stop right there. Once I've got those 4 factors down, I'm done. And it turns out that this means that there are 1,680 different ways that we can do this if we choose just 4 letters.
6 of the letters are used, and the word must begin with a Q.
Okay, now with a question like this, what we want to do first is start with the restriction. So the restriction in this case being that we have to begin with a Q. Well, how many Q's do we have to choose from in the word equation? Well, there's just 1, which means our first letter, the first task we have to accomplish here is getting that first letter. There's only one way to do that. Now, beyond that, we've got 5 other letters to throw in there. So 1, 2, 3, 4, 5. How many choices do we have for that second one? Well, 7. And then 6, and then 5, and then 4, and then 3. And when we multiply that all together, we're going to get 2,520 different ways that we can accomplish this goal, starting with Q.
5 letters are used, and a vowel must be at the front and a consonant at the back.
Okay, now in this case here, we're gonna start with a vowel, okay, and we have to end with a consonant. Now, we've got to take a look at that word equation. How many vowels do we have? Okay, E, U, A, I, O. 1, 2, 3, 4, 5. We got them all there. Okay, well, except for the sometimes Y. But anyway, so we've got 5 to choose from for that first position. Now, we're going to use 5 letters total, so 1, 2, 3, 4, 5. But our restrictions are on the first and the last position here, so we want to start with those. The restriction at the end here is that we have to end with a consonant. Now let's go take a look back up at the word equation. I've got 3 consonants to choose from, Q, T, and N. Whoops, it's right here. So that means I've got 3 choices there. Now, out of those 8 letters, once I've chosen those 2, now I've got 6 left over, and then I'll have 5 choices, and then 4 choices. All right, and so now the product that we're going to get is 1,800. Okay, 1,800 different ways that we can arrange these letters, starting with a vowel, ending with a consonant.
3 letters are used, and they must be made up of all consonants or all vowels.
Okay, now here's the first time we're running into this sort of a situation here, where we've got this 2 different ways that this particular question could be answered. It could be answered with vowels, or it could be answered with consonants. Now, if we do this with vowels, okay, remember what we had here. We have to put down 3 letters here, okay. And in this case, it's all going to be vowels. So for the first one here, I've got 5 choices. So this is going to be a vowel and another vowel, and I've got 4 choices and another vowel. Okay, 3 choices for those for that. Vowel right there. Sorry, I'm thinking ahead here. Anyway, vowel and vowel and vowel. Multiplication always implies the word and, or suggests an addition here. So we could do it with vowels, or we could do it with consonants. And there were only 3 consonants, so I've got 3 choices for the first one, and then I have to choose another one, and there's 2 choices left over, and then there's only 1 choice left over there. Okay? So here's our consonants. Okay, so vowels or consonants. So we want to associate, we'll write this over here, we want to associate multiplication with the word and, addition with the word or. And if you're ever in a problem here and you're kind of stuck and you're thinking, well, I don't know whether I should be multiplying or adding, if you just talk it out like in your head, say it in your head, describe the problem in your head, and just take note of whenever you use the word and whenever you use the word or, and that will very likely be the correct way to answer this problem here. Now what have we got here? 5 times 4 is 20, times 3 is 60, plus 6. So 66 different ways that we can arrange the letters in this way.
How many license plates can be formed from 3 letters followed by 3 numbers?
Okay, so one of the things about this particular chapter that some of you are going to really enjoy and others of you are going to be really frustrated by is the opportunity for you to interpret questions. Okay, so for example here, the question is how many license plates can be formed with 3 letters followed by 3 numbers? Well, the thing that you got to bring to the table here is, are you allowed to repeat these symbols on a license plate? And the answer to that is yeah, you can. So the number of tasks that we have to accomplish here are 6. Okay, 3 letters and 3 numbers. So how many options do we have for the first position on the license plate here? Now this is always entertaining to me because it's funny, and I don't exactly know why it happens like this, but if you ask people how many letters are there in the alphabet, most people tell you 26. However, there is a substantial portion of the population that will immediately spit out the number 24. Okay? So you need to be careful with these questions here that you get the right number. I suspect on a major exam there's going to be a lot of people singing in their heads A, B, C, D, and counting on their fingers to make sure this is correct here. But it's 26. You've got 26 options for the first symbol here. And for the second symbol, you've got another 26 options because you can repeat digits here, repeat symbols here. 26 for the third position. Now, as soon as you go to numbers, how many different digits are there? 10. Okay, 10 different digits. And again, we are allowed to repeat here. At least you are on a license plate. Now there are actually some rules about the things that you can put on a license plate, but we're not really concerned about that right now. Just based on this information and what you know about license plates, how many are possible here. And when you multiply that out, actually you get a crazy big number. You get 17,576,000 different license plates that you can create.
How many license plates can be formed with 3 different letters followed by 3 different numbers?
Okay, so now in this question right here, we eliminate that little bit of interpretation there because we're telling you that you have to use 3 different letters followed by 3 different numbers. So again, we've got six subtasks to accomplish here. 3 letters followed by 3 numbers here. I've got 26 options for the first one, and then my number of options decreases by 1 and then decreases by 1 again. So 26, 25, 24. I've got 10 different digits to choose from, and then it decreases by 1 and then decreases by 1. Okay? And altogether, when you multiply that all out, you still get this crazy big number, 11,232,000. It always impresses me how quickly these things grow.
How many 3-digit numbers can be formed from the following numbers? 2, 3, 6, 7, and 8.
All right, now for this question right here, one of the things that you have to know about the curriculum and the intention of the curriculum here is that when we give you numbers, when we ask you to create a number, okay, digits can be repeated. Okay? We want you to assume that digits can be repeated unless told otherwise. Okay, so that's worth writing down. Unless you're told otherwise, you need to assume that if you're using digits to create a number, that you can repeat them. However, and maybe I'll come down here and write this, letters cannot be repeated. Okay, cannot be repeated unless told otherwise. Okay, you're supposed to you're supposed to think about the letters as if they're on Scrabble tiles, and you can't repeat Scrabble tiles. The tile that you got is the tile that you got here. However, most of the applications with numbers, it makes perfect sense if you can repeat the digit here. So in this particular case here, notice that we've got 1, 2, 3, 4, 5 different digits that we can choose from. Okay, but I can repeat. So I'm going to create a 3-digit number here. That means I've got 3 subtasks here. There are 5 options for the first subtask, then 5, and then 5, because I don't lose options at any step here. I've always got the same number of choices for each step here. That means altogether I could create 125 different numbers from the digits that they gave me.
How many 3-digit numbers can be formed from the same group of numbers if repeats are not allowed?
And now once again with the problem here, we take a look at it in a slightly different way here. It's the same thing, same question, except now we're told that repetition isn't allowed. And again, if that's the intention of the problem, they have to say it, or you'll assume otherwise. So again, we're coming up with a 3-digit number. Okay, so those are my 3 subtasks here. I do have 5 choices for the first digit. Okay, once I've chosen that digit, now because I'm not allowed to repeat, I lose an option, and then again I lose another option here. And so that means altogether there are 60 different numbers that I can create with those digits.
How many 3-digit odd numbers can be formed from the same group of numbers if repeats are not allowed?
All right, this question introduces a restriction here. The restriction is that the number has to be odd that I'm producing here. So again, I've still got 3 tasks or subtasks here. And now I've got a restriction here. I want the result to be odd, so I got to look at the last digit here. Now, of that little group that I'm working with, the 2, 3, 6, 7, and 8, only 2 of those digits could be used to create an odd number, 3 and 7. Okay, if the last digit is either 3 or 7, there's 2 options there. Okay, that will give me an odd number as a result here. Now, remember, just to kind of regroup here so that we remember what we're doing here, when I'm filling in the numbers here, what these refer to, this 2 refers to 2 options that I have for that position. Okay, this is not like I'm choosing the number 2. There are 2 options for this position. Now, once that's chosen, okay, because we had 5 numbers to choose from, the restriction doesn't influence the first 2 digits here. So now I've got 4 options for the first digit and 3 options for that second digit. Okay? And then you multiply those all together, because in order to complete a number here, I need the first number and the second number and the third number. And so altogether, what we get here there are 24 different 3-digit odd numbers that I can create from the digits that are provided.
How many 3-digit even numbers can be formed from the same group of numbers if repeats are not allowed?
Now this question is really just in many ways, just the opposite of what we just did. Instead of coming up with an odd number, we're going to come up with an even number. Again, we've got 3 subtasks to accomplish here. And because there's this added restriction that the number has to be even, this digit right here has to be even. And out of that group, there are 3 digits that we could use to make this an even number. Okay, it could be the number 2, 6, or 8. Any of those would make this an even number here. Once that's chosen, because repetition again isn't allowed, I've got 4 options for the first digit and then 3 options for that second digit. Multiplying those together, we're going to get that there are 36 different even 3-digit numbers we can create.
How many 4-digit numbers are there?
All right, now this question right here is an interesting question, because the purpose of it is that so that we can have a conversation about building numbers. Okay, and there's a restriction, there's an implied restriction when you're building numbers. Okay, so how many 4-digit numbers are there? Well, okay, to build a 4-digit number, there are 4 subtasks that we have to accomplish here, okay, or have to finish here. There is a restriction here on the first digit. Okay, the first digit can't be 0. Okay, the number, for example, the number 023 is just the number 23. A 0 up in the front doesn't do anything, doesn't influence the digit, the number there. So we can't allow there to be a 0 up front here. So that means there was only 9 choices for that first digit. Now, beyond that, it doesn't matter. Okay, I've got 10 options here, and remember, this question does not tell us that I can't repeat the digits. So I have 10 choices, followed by another 10 choices, followed by another 10 choices. And so altogether, there are 9,000 four-digit numbers. Now, don't let that throw you off here, because I sometimes people think, well, wait a minute, no, there should be more than that. The first set of numbers up to 1,000 here are not four-digit numbers. A lot of times the confusion comes, even though we've just stated that you can't start with 0, people then assume, well, wait a minute, what about 500? Well, 500 is a three-digit number. Remember, the restriction is four-digit number. Okay, so yeah, there are just 9,000 four-digit numbers.
How many four-digit numbers are there if repeats are not allowed?
All right, here's another really interesting question, and I want you to really pay close attention to what happens in the second position, okay? So, four-digit numbers. So again, those four subtasks here. Again, there was that implied restriction on the first digit. You can't start with 0. So, there are 9 choices for that first digit. Now, I can now use 0 in the second position, which would mean, like in the previous question, there should be 10 options here. However, in the second position, I can't use the number that I just started with, because we are told here that repeats aren't allowed. So I don't know what number I used up here. It wasn't 0. Let's just say it was like 7. I can't use 7 here, but I can use 0. So I don't have 10 choices. I have 9 choices. Okay, I can use 0, can't use whatever I use up front here. Now, by the time I get to this position, 2 digits have been used, which means now I've only got 8 options for this digit here. Over here, 3 digits have been used, so I've only got 7 choices for that last digit there. And when we multiply those all out, we're going to get that you've only got 4,536 different numbers, four-digit numbers that can be produced that don't have repetition.
How many four-digit odd numbers are there if repeats are not allowed?
Okay, so again, four-digit number, 1, 2, 3, 4, so 4 digits. Those are our 4 subtasks. This time, though, we're throwing in the stipulation here that it has to be odd. That's a restriction on the last digit. Now let's think about it. How many of the digits can we put at the end of an odd number? Well, we could put 1, 3, 5, 7, 9. There are 5 choices. Okay, so we're going to start with the restriction that's overtly mentioned here. 5 choices for that last digit. But I can't repeat. Okay, I cannot repeat them. So now I'm going to move to the front. I can't use whatever digit was here. So I would normally have 9 choices here for this first digit. But I can't use 0. Okay, 0 wasn't even an option here, so 0 didn't even factor into this. But I can't use whatever digit I used here, and I can't use 0. Now, that's 2 digits that I can't use in this front position. That means there's only 8 options here. Now, once I move to the second position, 0's not an option. 0's not an issue. I gotta have 0 if I want. Yeah. What I can't use are the 2 digits that I just used. So that's actually interesting, because that means there's 8 choices. Okay, you're going to see this pattern show up quite a bit here, where I'm using the same number twice. And again, it's because of the 0, because it's not an option here, but it can become an option here. In this third position, okay, I've already used 3 digits, so that means there's only 7 options there left over for that third digit. Multiplying that all out, we get 2,240.
How many four-digit even numbers are there if repeats are not allowed?
All right, this question here is probably one of the more difficult questions that we can ask in this particular chapter, in this section, I should say here. Now, then I'll lead you through this here, and you'll see what I mean in just a second here. How many four-digit even numbers? So 1, 2, 3, 4. Okay, now it's going to be even. So now an even number can end with 0, 2, 4, 6, or 8. So there are 5 choices here for that last digit. Now, how many choices are there for the first digit? And I want you to think about this for a second, because you know what? this ends up being problematic. How many choices are there? It turns out it depends. It depends on what you chose here. Are there 9 choices or are there only 8 choices? Okay. Now, some of you are going to see the 9 because you think, well, if I chose 0 here, if I chose 0 to end it, then there's 9 choices right there. And you're right. For those of you that are seeing 8 choices, you're thinking, well, what if I chose 2? Well, then I can't use 2 because I've used it up, but I also can't use 0 because I can't start a number with 0. That's 2 options I can't use. That leaves me with 8. Well, you're right too. Okay, you're both correct. So because I can achieve this goal here in 2 different ways here, this is an OR question. Okay, in this case here, this is going to end in 0. And I'm going to do this in another way here, 1, 2, 3, 4. And this one doesn't end in 0. Okay, so let's take a quick look at this. If I end in 0, that means I've got 1 choice for that last digit. Okay, 0. Now, because the 0 is chosen, it's not an issue. Okay, for that first digit here, I don't even have 0 to choose from. So all of the other 9 digits are available. And then once those 2 are chosen, I've got 8 choices for that second position and then 7 choices for the third position. Or I choose to not end my number in 0, which means it could be either 2, 4, 6, or 8. That's 4 choices. So I've chosen a number. I don't know which digit it's going to be. I've chosen that number. So now I've got 9 other digits that I can choose from, but I can't choose 0. So that means there's only 8 that I can choose from for this position. Now, beyond this point, there's no restrictions. So all I got to look at here is, well, I've chosen a number for here, I've chosen a number for here. There's no more restrictions, so that means I've got 8 choices for this position, and then 7. Okay, and when you multiply that all out, you're going to get 2296, okay, different even numbers that don't have repeated digits.
How many 7-digit phone numbers can be formed with the following restrictions? The first number must be either a 4, 6, or 2. The second and third number must match each other. The last digit can be anything from 1 to 5.
Okay, this is kind of an interesting scenario here. 7-digit phone number, so that means we've got 7 subtasks. 1, 2, 3, 4, 5, 6, 7. 7 subtasks. Okay. Now the first one is going to be accomplished by choosing the number either 4, 6, or 2. Well, there are 3 options for that. Okay. Now, by the way, one of the things we got to come to this with is this understanding here that on a phone number, okay, numbers could be repeated. So that's just something I have to consider here as I go through this, because if I end up with a spot here where there doesn't seem to be any restriction on it, then I got to remember that these digits can be repeated, and so all of the digits are viable choices here. Now, it says here that the second and third number must match each other. Now, it doesn't say what they are, just that these 2 digits have to be the same. So I don't know what this first one of the pair should be, so there's 10 choices for there, but once I've made that choice, there's only 1 choice for that second one. It's the exact same one. Now, beyond that, I've got a section here where I've got some choice here. Okay? This could be 10 digits there, 10 digits there, there's 10 different digits that could go there. Right? There's 10 different choices for each of those. Because there's no restriction, there's no mention of what should go there, and I can repeat them, so away you go. Now, it does say, however, that the last digit here has to be anything from 1 to 5, and that means there are 5 choices there. And when you multiply that all out, you're going to get 150,000 different phone numbers that have that restriction, those restrictions, I should say, imposed on them.
Using the digits 0, 2, 3, 4, how many numbers can be formed if repeats are not allowed?
Okay, so let's take a look here. How many numbers can be formed if we're not allowed to repeat the digits? Okay, so we've got 1, 2, 3, 4 digits that we can throw in there. Now, thing is, can't start with 0. They threw a 0 in here, can't start with 0. So that means there's only 3 choices. That's right, can't believe I did that. I said 3, wrote 4. there are 3 choices for that first digit there. 1, 2, 3. Now, once you've chosen one of those, remember beyond that point there's no restriction. So there should be no restriction here other than the fact that I've already chosen a digit. So from the 4, that means there are 3 choices here. Okay, because I can't choose this one. After those 2 are chosen, there's 2 more choices, and then I got 1 more choice there. Now, you might think, oh, well, okay, there it is. I'm done. The answer is, what is that, 18? However, you made an assumption there. If you think this is the end of the problem, you've made an assumption that's not true. The question says how many numbers can be formed if repeats are not allowed. Well, if you stop here, you've assumed you meant a 4-digit number. It didn't say that. What about a 3-digit number? Okay, well, a 3-digit number is going to have the same sort of structure here. I have got 3 choices for that first digit, and then just like before, 3 choices for the next one, and then 2 choices for that, the 3rd digit there. So it could have been a 3-digit number. Or it could have been a 2-digit number. Okay, 3 choices for the first one, and then 3 choices for the next one. Or it could have been a single-digit number, in which case there's only 3 options. Well, sorry, that's not true. Sorry, 0 stands on its own. We can do that, which means there was 4 options for that last one. So 2-digit, and then a 1-digit number. Okay, now putting that all together, what have we got here? This is 9. 3 times 3 is 9 times 2 is 18. Another 18, that's 36. 36 and 9 is 45. And 4 is 49. So there are 49 different numbers that we can make given those restrictions.